Welcome to The Explainer. Today, we're diving into a really fascinating chemical case, a molecule that pretty much forced scientists to rethink the basic rules of a chemical bond.
So this question really gets to the heart of a puzzle that had chemists scratching their heads for years. I mean, think about it. Imagine you're building something, right? But you run out of screws or glue halfway through the job. What do? Well, chemistry faced this exact problem with a molecule called diborane.
Okay, so our story really starts with the element boron. It's the fifth element on the periodic table, and, it has this fundamental problem that kicks off this entire mystery.
Right, so in most simple molecules, atoms are happiest when they have a stable set of 8 electrons in their outer shell. You might remember it, it's called the octet rule. But when boron bonds with 3 hydrogens to form a simple molecule called borane, or BH3, it's left with only 6. This electron deficiency makes it incredibly unstable, kind of like a wobbly table that's just missing a leg. Yeah, because it's so electron poor and unstable, a single borane molecule is just constantly looking for a way to complete itself. And what's the simplest solution? Well, it finds another unstable borane molecule, and they desperately team up in a process called dimerization. So when these two borane molecules combine, they form a new molecule called diborane, B2H6. Now, this solves that immediate instability problem, but in doing so, it creates an even bigger structural puzzle, and this is where the plot really thickens. Let's do a little bit of chemical accounting, just to see why this thing is so weird. Okay, so each of the 2 boron atoms brings 3 electrons to the table, and each of the 6 hydrogens brings 1. That gives us a grand total of 12 electrons to work with. Now, we use 8 of those right away to form the 4 normal, sturdy bonds on the outside of the molecule. That leaves us with just 4 electrons. And here it is. Here's the mystery. We still need to connect the 2 boron atoms and the 2 hydrogens stuck in the middle. That's a framework of 4 atoms. Now, a normal chemical bond needs 2 electrons. So to connect these 4 atoms in a line, you'd need 3 bonds, which means you'd need 6 electrons. But we only have 4. The math just doesn't add up. Where did the other 2 electrons go? The answer isn't a mistake in our math. It's a brilliant and totally unconventional type of chemical bond that just breaks all the standard rules we thought we knew. The solution is this radical idea, the 3-center 2-electron bond. So instead of using 2 electrons to stick just 2 atoms together, diborane uses those same 2 electrons to connect a whole bridge of 3 atoms, a boron, a hydrogen, and then the other boron. It's like the glue is just smeared out over a much longer distance. And this creates a really stark contrast in the types of bonds. A normal bond is, a strong direct connection between 2 atoms sharing 2 electrons. But this new bridge bond, it's weaker, it's more spread out, and it's holding 3 atoms together with that same pair of electrons. It's an incredibly efficient, if a little strange, solution. And because the path of those shared electrons actually arcs out in this curved shape, kind of above and below the molecule, chemists gave it this fantastic and super memorable nickname, a banana bond. It's actually a great way to visualize this spread out, delocalized cloud of electrons. So this really unconventional bond ends up building a truly unique molecular structure, and it has these huge consequences for the molecule's final shape and all of its properties. And the result of all this is that the diborane molecule has 2 completely different kinds of hydrogen bonds. You've got the 4 terminal hydrogens on the outside that are held by short, strong, conventional bonds. But then you have the 2 bridging hydrogens in the middle, and they're held by those longer, weaker, 3-center banana bonds. This whole unique setup forces the molecule into a very specific shape. And get this, the 2 boron atoms aren't even directly bonded to each other in the way we usually think of it. Instead, they're only held together by those 2 hydrogen bridges, one arcing above and one arcing below, kind of pinning the whole structure in place. So why does any of this matter? Well, those weak electron-poor bridges, they're basically the molecule's Achilles heel. They are sites of chemical reactivity. Other molecules can easily come in and attack and break these bridges, which is what makes diborane a very useful, even if it is very reactive, chemical in fields like organic synthesis. Now, this elegant theory didn't just appear out of thin air.
It was a genuine scientific mystery that was pieced together by brilliant minds over the course of several decades.
The first really big idea came from H.C. Long J. Huggins way back in 1943, who proposed this three-center bond model. But it was William Lipscomb who, starting in the 1950s, used these powerful X-ray techniques to actually see the molecule's structure, which proved the theory was correct. His work ended up systematizing the entire field, and yeah, it earned him the Nobel Prize in 1976.
So ultimately, what you should take away from all this is that Diborane is way more than just a weird molecule. It's a perfect example of how science actually works. It shows that even the most fundamental rules, like, one bond needs two electrons, can have these incredible and really elegant exceptions, which kind of makes you wonder, what other rules are just out there waiting to be broken?